Hello, this is Tim Smith, the Academic Support Coordinator for St. John's River State College, St. Augustine campus. This video is part 3 on applications of integration and is designed as a study aid and supplement to the math tutoring services offered at St. John's River State College. It is recommended to view applications of integrations part 1 and 2 prior to watching this video. In this video, we will be discussing the length of curves and work. Suppose we had a function f of x continuous on the interval a, b. If the function creates a straight line, the length d from the points a f of a to b f of b is easily calculated as d equals the square root of b minus a quantity squared plus f of b minus f of a quantity squared. A curved line makes this problem a bit more difficult. If we partition the arc in the same manner as we did to derive an integral, we can determine the length in the same manner. The length from the distance formula of any segment is the square root of delta x squared plus delta y squared. The length of the entire segment is then the sum from I equals 1 to n of the square root of delta x squared plus delta y squared. We force a factor of the delta x squared term, which will give us delta x squared times the quantity of 1 plus delta y over delta x squared under the same radical. The mean value theorem states that there must be a c for which f prime of c equals the average rate of change, so we can replace delta y over delta x. We can also move the delta x squared outside the radical as delta x, giving us a sum from I equals 1 to n of the square root of 1 plus f prime of c squared times delta x. When we put this in integral form, we get length is the integral from a to b of the square root of 1 plus f prime of c squared dx. Let's try an example. Let's find the arc length of f of x equals x to the 3 over 2 on the interval 1 to 8. F prime of x is 3 over 2 times x to the 1/2. The length will then be the integral from 1 to 8 of the square root of 1 plus 3 over 2 x to the 1/2 squared dx. When we take the square, we get the integral from 1 to 8 of the square root of 1 plus 9 over 4 times x dx. If we factor 1/4 out of the binomial, it can be removed from the radical as 1/2 and moved outside the integral as a constant. To simplify the integration, we let u equal 4 plus 9x and du equal 9 dx. When u replaces x inside the integral, the boundaries must also change. So we solve u equals 4 plus 9x for 1 and 8. This means the lower limit, we set x equal to 1, meaning u will equal 13. On the upper boundary, x equals 8, so u equals 76 for the new upper limit of the integral. Now the integral is 1/2 the integral from 13 to 76 of the square root of u times 1 over 9 du. 1 over 9 can be removed from the integral to get 1 over 18 times the integral from 13 to 76 of the square root of u du. Taking the integral gives us 1 over 18 times 2 over 3u to the 3 over 2 evaluated from 13 to 76. Which equals 1 over 27 times the quantity of the square root of 76 cubed minus the square root of 13 cubed. We can simplify to 1 over 27 times the quantity of 152 times the square root of 19 minus 13 times the square root of 13, or approximately 22.80 units of length. In physics, work is defined as the force acting on an object over a distance and is expressed using the units of Newton meter or joule. In English measurements, the units of foot-pounds is used. When that force F is constant and in one direction x, then the simple formula applies, W is equal to F times x. That formula assumes a constant force. The work done by a continuously varying force F acting on an object which moves along a straight line in the direction of f from x equals a to x equals b is work equals the integral from a to b of f of x dx. dx. As an example, how much work is required to wind a 30-meter long length of chain which hangs vertically from a cylinder attached to a winch? The chain has a mass of 5 kilograms. This requires a changing amount of force because the chain becomes lighter with each length that is wound into the winch. Again, the amount of work is force over distance. In this example, the force equals weight, which can be calculated as mass times gravity. Gravity is 9.8 meters per second squared times 5 kilograms. Then the distance is 30 minus x dx. 9.8 times 5 can be removed from the integral as constants. Then we take the integral, giving us 49.0 times the quantity of 30x minus x squared over 2 evaluated from 0 to 30. This gives us 49.0 times the quantity of 30 times 30 minus 30 squared over 2 minus the quantity of 30 times 0 minus 0 squared over 2. We can simplify to get 49 times the quantity of 900 minus 450, or 49 times 450, or 22,500 joules of work. Another example of work done by a varying force is work done by a spring. According to Hooke's law, the force exerted on or by a spring is proportional to the distance from its equilibrium point. The equilibrium point is defined as the position of the spring with no force applied to it. F is equal to negative k times x. In this equation, k is a spring constant measured in newtons per meter and is negative to indicate the force acting opposite to the direction of its displacement. The work done by a spring force when compressed from equilibrium to a distance a is the integral from 0 to a of negative kx dx. For example, given a spring with a constant of 150 newtons per meter, how much work is required to compress the spring 0.4 meters from its equilibrium point? According to Hooke's law, work in this case will be the integral from 0 to 0.4 of negative 150 x dx. Negative 150 can be removed from the integral as a constant. Then we take the integral, giving us negative 150 times x squared over 2 evaluated from 0 to 0.4. Or negative 150 times the quantity of 0.4 squared over 2 minus 0 squared over 2, or negative 150 times 0.16 over 2, simplified to negative 150 times 0.08 or 12 joules. The negative implies work in the compressed direction, which would still be 12 joules whether we compress it or expand it. Another example of work done by varying force is the work done to pump a liquid out of a tank. This involves a variable force due to the idea of pumping liquid to increasing heights over time as the level in the tank decreases. In this type of equation, the work done, W, depends on the weight of the liquid, which is density times volume, times the acceleration due to gravity. For our changing volume, we use the area of the layer A, and the changing height of the water column h minus x, with h being the distance to the top of the tank. Since this distance changes as the tank is emptied, the force is not constant. Work is then the integral from 0 to h of pga times the quantity of h minus x dx. This will calculate the work needed to empty the tank or to take the height of the water to 0. As an example, how much work is required to pump all the water from a cylindrically shaped tank 12 meters in radius and 4 meters deep? We start with our integral and fill in the appropriate numbers. The density of the water is 1,000 kilograms per cubic meter. Gravity is 9.8 meters per second squared. And the area of the layer of the volume is 12 squared times pi. And the varying height of the water level is from 0 to 4 meters, or the integral from 0 to 4 of 9800 times 144 pi times the quantity of 4 minus x dx. 9800 times 144 times pi can be brought outside the integral as constants, giving us 1.41 times 10 to the 6th power times pi times the integral from 0 to 4 of 4 minus x dx. Taking the integral, we get 1.41 times 10 to the 6th times pi times the quantity of 4x minus x squared over 2 evaluated from 0 to 4. Well, 1.41 times 10 to the 6th pi times the quantity of 4 times 4 minus 4 squared over 2 minus the quantity of 4 times 0 minus 0 squared over 2. We can simplify to get 1.41 times 10 to the 6th pi times the quantity of 16 minus 8, which is 8, or 3.55 times 10 to the 7th joules of work. If you have further questions on this or any other math topic, or wish in-person tutoring, please consult the Academic Support Coordinator on your respective campus. Thank you, and good luck with your studies.